Hello, hello. Is my voice clear, Vinod, Krishnendu?
Yes.
Okay, thanks.
Yes.
Huh? Topic क्या है? Syntax-Semantics Dualities. हमारा डिसाइड हुआ था ना? हाँ. वन क्यों चाहिए? 5 पे आने रहेगा. अच्छा. हाँ. अनाउंसमेंट चाहिए. हाँ, मुझे लगता है अनाउंसमेंट सेकंड टॉक मतलब सेकंड टॉक के शुरुआत में होना चाहिए या इसके एंड में होना चाहिए. पीपल डोंट जॉइन. ओके. If you could wait today until 5:15, there is a group photo. Yes. Okay.
हेलो हेलो
हेलो. ये कौन? तुम बोल. So some of the speakers have already requested everybody to switch on their videos, but then they write on the board, so they can't see you. And that's why I'm standing here, so that I can see all of you. Is my board entirely visible or not? How much can they see on here? Because maybe the whiteboard is too big. I have to optimize it for this purpose. That's okay. Okay. If I write here, then that part will be cut for the offline participants. Yeah, that will happen.
Okay.
Project here. I mean, I don't have slides. I'm going to write using this pen. Yeah. Yes.
I'll just say that.
Yeah.
Or anything else.
No, that's okay. Generally in online classes, I used to say that I'm not going to talk to an empty room. Yeah. So I cannot see, if I see all the black faces, then I cannot do that. Here I have got a live audience, but I still want to treat all of you as the real audience. So as much as possible, if you have not just woken up, please switch on your video. The image of a person is only clear if you know who they are. If you look at their face, then you sort of understand whether they are getting your point without them telling you explicitly.
Why do I get a white screen? I'm not.
Yes, there is a white screen because I'm going to write on the white screen.
Okay.
Yes.
This is what I will see.
Yes. You need to spotlight this.
Huh?
You have done that?
No, I'll do it.
Yeah.
Good morning, everyone. So we'll begin with our first session. So we have Dr. Amit Kuber here. He is a faculty member of the Department of Mathematics and Statistics at IIT Kanpur. His current interests lie in combinatorial aspects of representation theory of string algebras. And his long-term interests lie in the foundational areas of mathematics, including category theory, logic, and model theory. So today he'll be speaking about syntax-semantics dualities. The stage is all yours.
Okay. Thanks a lot. Okay, so this particular topic, I hope I'm clearly audible here. This particular topic is a mixture, an amalgamation of all the things that you have seen so far. I'm going to talk about logic, syntax and semantics. These are the words used in logic. Then I'm going to use category theory heavily. This is categorical syntax semantics dualities. I will also refer to topological spaces occasionally. Orders, Boolean algebra are always our friends. So all of these things will come together in these talks. And if you have not understood any of the previous parts, then you have to let me know, because it is very important to get that for these lectures. The topic today that I have chosen, at least for the first half or so, is that of stone dualities. So you already heard 2 lectures on stone dualities, but I want to give you a more categorical, more syntax semantics feel of the of stone duality. So category theory is extremely important while we are doing this. And I want to start with something which is really very simple, and that is our exponential arithmetic. Is my font okay for everyone? Offline participants? Yeah? Okay. So exponential arithmetic is something which we all know. So suppose I start with 3 real numbers. Then I can write down some exponential laws like this. So if I take b times c, and if I raise it to the power a, what will I get? This is not a one-way presentation. I'm standing here for a reason. Please answer these questions, simple questions. B to the a into c to the a. Okay. Very good. Then what if I write a to the power b plus c? A to the b times a to the c. Okay, good. Then what if I write a to the power 0? Okay, then 1 to the power a? 1. Okay. So these are the 4 properties. There is one more which says a to the 1 is equal to a, but I don't want to use that because that will not be generalized to what we want to see. Okay, so now this is the exponential arithmetic with real numbers. Now I simply want to change the same exponential arithmetic to 3 sets. So I should not say this, not belonging to real numbers. I should say that belonging to sets. So if I'm given this kind of thing, then I will write down these same identities where dot is replaced with product. So I will say b cross c and to the power a. So this to the power a is nothing but the set of functions from a to b cross c. Equality, when I'm talking about sets, will be replaced by bijections and b to the power a cross c to the power a. Similarly, I can write down a to the power b disjoint union c is isomorphic to a to the power b cross a to the power c. Then I can write down a to the power empty set is isomorphic to 1. 1 is the singleton. Yeah, empty set is 0. So you have seen already that empty set will play the role of the initial object in the category of sets, which means from initial object to every other object, there is a unique morphism. Yeah, so if you are confused about this, think about the empty function. A function is given by the rule. Yeah, I mean, it is a subset of a cross b, function from a cross b, where to each element of a, there is a unique element of b associated with it. Okay, so this is what we are
Excuse
trying.
me, sir.
Yes.
So what is this set power set? How do we say it
power
numerical?
set? Yes, I will write it for you. Thank you. If you are not clear, it should be clearly mentioned. So home sets AB is the short form for b to the a. It is the set of all functions from a to b.
Okay, sir.
Yeah. Okay, so similarly, terminal object in the category of sets is the singleton set. Right. And last property was that if I take all functions from a to 1, then they are in one-to-one correspondence with 1 itself. Right. Now, if you have understood this part, then I want to rewrite these things in a slightly different language. So let us see. The first property that I can write down, home sets A, B cross C is isomorphic to home sets AB cross home sets AC. Is this clear? This is simply a rewriting of what we already know. And here you can see that this particular identity actually tells us that the functor, the covariant home functor, home A blank, it preserves products. There is this first product and there is the second product. So this says that home sets A blank from sets to sets preserves products. Now let us try to, any questions about this? That this functor preserves products, it takes products to products. Okay, so let us try to look at what is the second one. Okay, so the second one is going to say home sets B disjoint union CA, which is the co-product. Yeah, disjoint union is the co-product in the category of sets and is isomorphic to home sets BA cross home sets CA. So this does this look like any preservation property at all? Can anybody interpret this result for me?
Yes, so the contravariant functor home.
Contravariant home functor, yes. What does it do?
It will preserve co-product.
No, it doesn't. The convention is that, so let me write it over here. So home sets blank A. Yeah. Now this is a contravariant functor, but I may as well treat it as a functor from on sets op.
Right.
Yeah, as a covariant functor and map it to sets. Then what is the duality principle? Yeah, this is about, this school is about logic and dualities. This is one easy kind of duality. It's an abstract duality. The duality principle says that if you reverse all the arrows, then limits will become co-limits. Co-limits will become limits. So in that sense, this particular functor, this symbol here, yeah, the disjoint union symbol, that disjoint union is happening inside sets. It is a co-product. It is a binary co-product in the category of sets. So in the opposite category, it is actually the product. And therefore, what we are saying once again, that this functor from the contravariant home functor, when treated as a covariant functor on sets op, it is still taking products to products. Okay, so I'm just going to write that it preserves products. Is this point clear?
What is the difference exactly between both the statements? I understand this. I
Domain
understand
category.
this.
The domain category is different. That's all. There is no difference.
Okay.
So one thing one has to remember about the home functor is that it is a bifunctor. It takes two arguments and it outputs one. In the first argument, it is order reversing. It is contravariant. In the second argument, it is order preserving, which means, in other words, it is a functor from sets op cross sets to sets. But what we are claiming here, that in both the arguments, it preserves products. Is that clear? Okay, so let's go ahead. There are a few talkative people. I have been hearing their voices for last 3 days. Other people should also talk if they have any questions, because when people don't talk, there are only two possibilities. Either they understand everything or they understand nothing. Okay, so if you don't wish to be categorized in these two categories, then you better talk.
Excuse me, sir.
Yes.
So in the second example,
Right.
like which where the op is preserves products. So could you please explain that once again?
Yes. So the highlighted disjoint union symbol, that is a binary coproduct in the category of sets. which means by duality principle, it is the binary product in the category of sets op, in the opposite category of sets. And now what I'm claiming, yeah, this I can replace, if you wish, I can replace this by this symbol cross op, which means the product in the opposite category. So the binary product is mapping to binary product. That's all it's saying.
Oh, okay, understood.
Okay, now before I move ahead, do you want to see what this last identity says? 1 to the power a is isomorphic to 1.
Like there is only one mapping from a set to a singleton set.
Yes, but what can you say about the functor home a blank?
It preserves initial terminal
Yes.
object.
Home a blank will preserve
Yeah.
terminal. So terminals are limits. Binary products are limits. In a similar way, you can check that not just binary products, but arbitrary products will also be preserved. Arbitrary Cartesian products of sets will also be preserved. And not only that, the equalizers will also be preserved. So in general, I can make the statement, these are all limits. So I can make the statement that all limits are preserved by the home functor. Okay. In both the components, all limits are preserved. I'm going to tell you, yeah. So if you do analysis, then a function preserving limits, we call it continuous. So we are allowed to use this word, that a functor which preserves all limits, we can call it continuous. It's a continuous functor. Or if it only preserves binary products and equalizers, then we call it a Cartesian functor. Okay, Cartesian or finite limit preserving functor. The dual version is called a co-continuous functor. There is also a funny name of a paper on category theory. I know the author as well. So are ends and co-ends your friends? That's the name of a paper. Yeah, so the word co is very much popular amongst category theories because they have to dualize everything. But this is not the kind of duality that we are focusing on in this series of lectures. This is an abstract duality. We are focusing on more concrete dualities where results can be transferred from one area to another. Anyway, coming back to the main topic. So a functor F from category C to category D is said to be a representable functor if there is some C in C such that home C blank is isomorphic to F. So the next session is on category theory discussion. At that time, I will discuss more about the philosophy of category theory. But for now, I just want to give you a flavor that inside any category, there are objects and morphisms connecting objects. Now you can think of categories themselves as objects. Then functors are the appropriate structure preserving maps between them. But then if I fixed source and target categories C and D, and then I take all the functors from C to D, then if I treat those functors as objects, then natural transformations become my morphisms. If you are an infinity category theorist, then the process will never end for you. That is what you are interested in. So the functors are called as one morphisms, then natural transformations as two morphisms. So between two morphisms, you will have three morphisms and so on and so forth. Okay, so that process will never end. But for us, yeah, we are ordinary category theorists right now. We will end the process at 2. Okay, so when I say that this home functor is isomorphic to F, what I really mean is that there is a natural transformation from one functor to another, which has a two-sided inverse. Okay, that's what.
Sir,
yes.
F should be from C to sets, right? Or D?
Oh, yes, thank you. You're right. Actually, I mean, this is not really necessary, but yes, you're right. For the purpose of this thing is correct. C to sets such that home. So this is the covariant representable functor. What will be a contravariant representable functor? It will be a contravariant functor which is isomorphic to the contravariant home functor. Right? So home blank C. If it is isomorphic to that, then we will also call it a representable functor. Okay, now enough of this abstraction in general. Now let us come back to stone duality. This is going to be my main topic of discussion today. If you remember what stone duality said, I'm going to draw the picture that we had yesterday. I will just have a bigger name, bool alg, that is the category of Boolean algebras and homomorphisms between them. And on the other hand, I have got the category of stone spaces. As you know, they are compact, Hausdorff, totally disconnected spaces. Yeah, these are stone spaces. And there was a stone dual functor from here to here. And the Klopen sets, right? So this is the Klopen blank functor. And on this side, you have the stone dual, which I'm again going to write as stone. So usually my category names are have an underline. So don't confuse this. This is stone blank. Yeah, this is the stone space associated with the Boolean algebra. And how did we obtain that stone space? Can anybody recall? Or was it too much material in one lecture and you don't remember anything?
A collection of prime filters of Boolean
Exactly,
algebra.
collection of prime filters. Very good, Sujit. So H. So let's say I'm going to use the letter U for filters. Okay. So U, subset of a Boolean algebra, is an ultra filter. I think you saw this in the tutorial. Is an ultra filter if if it is a filter, if it is a proper filter, and for all A belonging to B, exactly one of A and negation A belongs to U. Yeah, both of them cannot. Only one of them will belong to U. That's an ultra filter. The word prime filter has a slightly different definition, so I thought I might as well give you. So U subset of B is a prime filter if it is a proper filter and there is a property similar to the prime numbers. And for all AB in B, if A join B belongs to U, then either A belongs to U or B belongs to U. This is the property of being a prime filter. So in the case of Boolean algebras, the words prime filter, maximal filter, ultra filter, they all coincide. But as you will see later today, when Nick Bezanishvili will talk about intuitionistic logic and Eyting algebras, these concepts do not necessarily coincide. These are just different versions of this. Right. Any questions so far? So I want to just talk about, yes. Somebody is talking. Sujit. No. That was accidental, perhaps?
Yeah. That was accident. Sorry.
Right. So now if you are given a filter, so let us say that if I'm given an ultra filter, so given U subset of B, an ultra filter, this is the usual notation, ultra filter, abbreviation. We can define F from B to the two-element Boolean algebra by sending all elements to either 1 or 0, depending on whether that element belongs to U or not. This is a Boolean algebra homomorphism. That you can check very easily. Conversely, given any Boolean algebra homomorphism, the inverse image of the top element in 2 is always going to be an ultra filter. In other words, the set of ultra filters in a Boolean algebra is in one-to-one correspondence with home bool alg B two-element Boolean algebra. It's in the bottom right corner, which means I'm just going to use this opportunity. I can replace this stone blank functor or the set of ultra filters or the dual space functor by home bool alg blank 2. Now you can see why I was talking about representable functors. Because this stone space functor, associated stone space functor or dual space functor, is in fact representable. This is isomorphic to this. Any questions? Okay. If not, let us go ahead and
hello, sir. So if a part of an equivalence is a representable functor, then the other part also should it be representable?
Not true in general. I am not sure, like you can't necessarily prove such a result, but in this case it will happen.
Okay.
That's why it's a duality. It's a concrete duality, and I will say something more about it soon. Right. So what is the other thing? I'm starting with a stone space, and I'm simply going to associate to it the set of all Klopen subsets. The Klopen subsets of a topological space, they do form a Boolean algebra that you have seen already. But what are Klopen subsets? Given any Klopen subset, if Y is a Klopen subset of X, then you can define, associate to it a function f from X to the two element discrete topological space. I'm just going to write DISC, two element discrete topological space, where a point is sent to either 1 or 0 depending on whether it belongs to Y or not. You can check this is continuous because singleton 1 is continuous, so its inverse image has to be open. Sorry, singleton 1 is open, so its inverse image is open, and singleton 0 is open, so its inverse image is also open. So which means this is a continuous function. Conversely, given any continuous function to the two element discrete space, the inverse image of 1 is going to be open, and so is going to be the inverse image of 0. They partition your set, which means there is a one-to-one correspondence between Klopen subsets and homomorphisms from X to the two element space. So which means this is same as, this is in bijection with home in stone X2. So let us go back and rewrite this over here, that this functor is also going to be home stone blank 2 discrete. Okay, so now this is a reinterpretation of this particular stone duality, that you are starting with two categories, Boolean, the category of Boolean algebras and the category of stone spaces, and you have got a pair of contravariant functors, but there is something special about it, that as Bhargav already was asking, that you have both of them representable with the same object essentially. The object here is 2. Yeah, this particular 2, and the object here is also 2. So such objects are known as dualizing objects, which means the two element set plays a dual role here. It plays the role of a two element Boolean algebra as well as the role of a two element discrete topological space, which happens to be a stone space. Okay, so this is something important, that 2 is a dualizing object, and therefore this is a perfect duality. In more technical terms, we'll call that the stone duality is a perfect, two-sided duality with the dualizing object This can be made a bit more precise, but I don't think it is suitable for the general audience. What is the meaning of dualizing object? For now, like, it's just an object which has two different roles in both categories. Yeah, the underlying set is exactly the same.
I have a question.
Yes.
So here.
Yeah.
So you said that it's dualizing object 2. So, but 2 has different meanings in two different.
Yes, that's what I mean. The correct way, if you are asking me, is that there are two faithful functors down to the category of sets which agree, which have isomorphic images of this dualizing object. That's the correct meaning of that. Yes, any other questions? This is simply a reinterpretation of stone duality. Okay. In that case, let us proceed. Okay, so now we want to start looking at something called syntax-semantics dualities. And we'll say that The stone duality is an example of a syntax-semantics duality. So just some words about what syntax is, what semantics is. Purvita already mentioned something yesterday. I just want to add a few things. Syntax is something, it's like formal expressions which can be manipulated even by a machine because there are rules of inference. It's a no-brainer job. Yeah, once you feed it into a machine, you just follow the instructions, and then if there is some input, you will get some output. Whereas semantics, this word also has a deeper meaning in linguistics. Yeah, this is an English language word. Semantics stands for understanding, human understanding. Yeah. So, for example, I remember distinctly a quote from Professor B.V. Rao. In the last ISLA, when he was teaching, giving lectures on set theory, he said that our parents and primary school teachers have done a really good job, an excellent job of teaching us what numbers are, what colors are. So actually, you can't really define what is number 3. If you think about it, you know what is the meaning of 3 chairs, 3 tables, 3 persons, but you can't really define number 3. You have to go very abstract. But still, we all have number 3 in our common knowledge base. Similarly, if I use the word and, yeah, the English language word and, anybody who understands any language, they have a pretty good understanding of the word and. They won't confuse it with or. So we all have that. We cannot explain why, but we all have that common meaning in our brains. That is what semantics is. So the syntax and semantics are essentially 2 different ways of looking at the same abstract object. So if there is a theory, an abstract theory, then it manifests itself in 2 different forms. One of them is syntax, another one is semantics. And because that theory is still the same object, these are just 2 different presentations of that theory. That's why there is duality. Okay? Duality is the name, as you will see. If you are fond of science fiction movies, yeah, you sometimes touch a mirror and then go inside it. It's a totally different world. But everything is happening opposite over there. That is precisely what duality is. It's a different world. It's a different language altogether to talk about this. As you can see in the case of stone duality, it's a different world. Boolean algebras are different. Stone spaces are different. One class of persons is studying algebra, another class is studying topology. But still, they are 2 different manifestations of the same abstract idea. If you are interested in studying dualities further, then there is also a third vertex of this triangle, and where you can study the classifying objects of these theories. That's from that also you can recover both syntax and semantics. But let me tell you that, already Professor Mahua Banerjee has covered this completeness theorem. Yeah, on one side you have got proofs. On another side you have got validation or truth. Soundness theorem says that whatever that can be proved is true. And completeness theorem says that whatever that is true has a proof. Yeah, which is a non-trivial direction. It uses axiom of choice at some level. The syntax-semantics dualities, on the other hand, yeah, they go one step higher. We don't talk about proof theory. We have syntax, we have semantics, but we don't talk about proof theory. It's about extracting the common theory of all the structures which are models of a theory. Okay, maybe that sentence was a bit too abstract. All of you know group theory? Yeah? Yeah, group theory, it has some language. The language of group theory says that it has got a binary function symbol, as you saw yesterday in Purvita's talk. Binary function symbol, unary function symbol, namely inverse, and a constant symbol, which is a zero-ary function symbol, which is identity. And then you write down three axioms. There is associativity, there is identity axiom, and there is inverse axiom for inverse. So these are three different axioms. Now this is called the theory of groups. And actually the word group is a short form for the model of the theory of groups. Okay, this is a new way of looking at it, but it's the model of the theory of groups. A ring is the model of the theory of rings. Yeah, that is how we look at things. So the theory of groups is more fundamental than group itself. So if I am given, if I am given this language of groups consisting of this binary, unary, and zero-ary function symbols, and then I ask what kind of sentences in this language, what kind of formulas in this language, which do not have any free variables, are true in all groups. Yeah, the sentences which are true in all groups. Then though that will be the collection of all the consequences, all the deductions of these three basic axioms. Anything that you can derive from these three basic axioms, those are all the sentences which are true in all groups. Conversely, if I'm given that theory, then I can talk about all the structures of this language where these axioms are true. So recovering the theory from the class of all its models is the basic principle of a syntax-semantics duality. Let me formalize that, but before that, I will take a sip of water. And if I say to you now that stone, yes, yeah.
Syntax is just an abstract sequence of words. Semantics is giving the meaning to that.
Yes.
And it can have different meanings.
Yes.
Like three is just a word.
Yeah.
Word, whereas you give many meanings to that.
Right. Yes.
Just a wonder.
Yeah, sure.
So first of all, how do you get that meaning?
So we generally don't manipulate semantics. We manipulate syntax in such a way that it tries to capture the meaning that we already have. Yeah, it somehow refers to our common knowledge base. So the proof system that Professor Mahua Banerjee was talking about, that is rigged. So you try to find out certain rules of inference, like modus ponens is so natural. If you are given A and if you know that B follows from A, then you can conclude B. This is in our understanding. So we put that as a rule of inference. And then we put a few more axioms. And then we ask, is it sufficient? So we generally manipulate syntax. We don't deal with semantics unless we want to, change our understanding of those words. So a logician will simply try to understand how we think. And that's the whole purpose of doing this. I'm not saying it's cognitive science, that's different. It's mathematical logic after all. But that's what we are doing. So on this side, I'm just going to say this, that Boolean algebras are the syntactic manifestations of propositional theories. Whereas stone spaces are semantic manifestations of propositional theories. Let me make it more clear. On the syntax side, you have got Boolean algebras, which consist of the equivalence classes, logical equivalence classes of formulas. Okay, logical equivalence classes of formulas. Formulas are syntactic objects. Logical equivalence classes, something which can be which is provably equivalent to a given formula, is something equivalent. So that means it is still a syntactic object. Whereas stone spaces, the elements of this stone space are valuations. The points of the stone spaces are valuations. Valuations are semantic. Yeah, you associate meaning. It's like this proposition is true, this propositional variable is false. So that is the semantic understanding. So let me make this a bit more clear. So say that now, again, I will start using the blue colored pen. So any questions about this abstract discussion so far?
Sir,
Yeah.
could you like in a one-liner give again the difference between syntax and semantic?
The definition between syntax and semantics, what does that mean?
Not the definition, I said the difference.
The difference between syntax and, okay, so syntax is something which is formal, something which can these are no-brainer rules. Yeah, you can teach them to a computer. It's manipulation of strings, it's manipulation of symbols, that's all. Whereas semantics is our understanding.
Oh, I get it now.
Okay. Okay, all right, let's go ahead. So say that sorry, I shouldn't say that. I first of all want to fix, using the notation yesterday, fix a set PV of propositional variables. I'm only going to work with a fixed set of propositional variables. I don't really care whether it is finite or infinite. I don't want to prove any representation theorem. Yeah, then if you remember, then F was the notation for the set of all formulas. Yeah, a set S subset of F is an inconsistent theory. Sorry, there should be no gap between these words. If for some P in PV, there is either a proof of negation P and P. Sorry. I can either use this symbol, I can use this other symbol. By completeness, they are equivalent, which means there is a proof of a contradiction. A contradiction follows from that set, then we say that this theory is inconsistent. Otherwise, we say it is consistent. So this is one of these definitions where you define the negation first. Script F is the set of all formulas, propositional formulas. Otherwise, we say S is consistent. Okay, so S is inconsistent if it can prove a contradiction. S is consistent if it cannot prove a contradiction. Yeah, defining inconsistency is more natural. And another thing, yeah, I mean, this is very simple. So given alpha in S, we clearly have a proof of alpha from S. Correct? Because you can deduce anything which you already know. Now, using this as the motivation, I will define the other way around, that say that S is deductively closed if whenever alpha follows from S, or alpha can be deduced from S, then actually alpha is already in S. After 50 minutes, all the cameras are off except for Bhargav's. If you are a multitasker, then I really admire you. If you are listening to the lecture and doing something else as well. Okay, fine.
You're already given that alpha belongs to S.
No. This is an independent statement. These last two statements are independent. I showed to you that whenever alpha is in S, then you can always deduce it from S. Yeah, the converse is that if S is, we say that S is deductively closed if all its logical consequences are already inside it. They are trivial consequences. That is deductively closed. Right. Any questions about this? These two are independent statements. Consistent and inconsistent theories. Okay, let's go ahead then. Now, I'm going to use consistent theories. Yeah. And on one side, and on the other side, I'm going to use classes of structures. Now, here the word structure actually refers to valuations, which means I have fixed the set of propositional variables. Whatever valuations I have, I'm simply taking its subsets. Okay.
Some maps from formal symbols to
from PV to 2. Equivalently, they are maps from F to 2. Equivalently, they are maps from F modulo logical equivalence relation. They are Boolean algebra homomorphisms from F mod from that Boolean algebra to 2. And I'm saying these are just subsets of, but I'm using this word for a reason. Yeah, the word class for a reason. Because even when I go to the first order theories, I will still continue talking about the same things. Okay, so I have got consistent theories. The completeness theorem actually tells us that a theory is consistent if and only if, yeah, theory is consistent. Let me write that. A theory S is consistent if and only if it has a model. i.e., there exists a valuation such that V of capital S is true. This is an abbreviation for saying that V of alpha is true for all alpha in S. So this is again Gödel's completeness theorem. Right. So if I go here now I can't find the list of participants. It's gone down somewhere. No, I cannot get the thumbnail. I have lost that image altogether.
Click on share.
No, it's here. Yes, here. Okay, I'll keep it here. Right. So consistent theories, given any consistent theory, if I talk about all its models, then I will get some valuation, some non-empty subsets of this. And on the other hand, if I will define this mod blank and th blank, this is the theory. So what is mod? So given S in subset of F, then I can associate to it the class of its models of S, which is the collection of all those valuations such that V of S is true. Conversely, if I'm given a set of valuations, or a class of valuations, then I can associate to it all those formulas which are true for all V in W. This is a very natural assignment, I suppose. Yeah? One more thing that you need to observe while you are looking at this.
W is a class of models or W is a model? I mean,
W is a class of
Okay.
structures. Yeah.
Okay.
Yeah. Structures are just valuations, so it is a set of structures.
Okay. Thank you.
Yeah. Okay. So this kind of assignment, you can see if I take S1 subset of S2, then what will happen about models of S1 and models of S2? This is contravariant, yeah, naturally. If I increase my set of axioms, then I have more restrictions and therefore fewer valuations will satisfy that condition. Simple idea. So this is naturally contravariance. Similarly, if I have W1 subset of W2, then theory of W1 will be bigger than theory of W2. So in this case, I'm simply, if I consider theories with subset relation and classes of structures with subset or subclass relation, then I have a contravariant assignment on both sides. So ideally, I should be writing an op over here, and then this will become a duality. Although it's not a perfect duality. So I want to give you a very general understanding of duality, that it's an adjunction. It's a dual adjunction. It's a contravariant adjunction. What is the adjunction here in this simplest case? It is simply an antitone-Galois connection that Animesh has already talked about yesterday. Now, what is the meaning of antitone? That these are order-preserving maps, which we have already seen. One more thing that you observe, if I start with some S over here, then I complete this cycle, then what I will get? I will get that S is contained inside the common theory of all the models of S. On the other hand, if I start with a class of structures, then also, if I take the models, all the models of the common theory of W, then that will be bigger. On both sides, it's going to be bigger. On this side, can you say something about this particular theory? Theory of models of S. Atri, I think you are gearing up to say something.
Actually, I thought ACE is closed. I think you have earlier said, no?
S is closed under what?
No, I mean, like
Okay. So if I have alpha and beta, yeah, alpha comma beta in S, then in every model of S, alpha meet beta will also be true. Correct? Because alpha is true and beta is true, alpha meet beta will also be true. And alpha meet beta is a deductive consequence, is a logical consequence of alpha comma beta. Even if it were not present there, it will be there in the common theory of all the models, which means this is going to be deductively closed. So Atri, you are close. Yeah, the word closed is still there.
Yeah, deductively closed. I missed that.
Deductively closed, yes. So S is contained inside the common theory of all models of S. On the other hand, I don't want to go into those details, what this is. I don't even know if there is a nice presentation for that. But that means the fixed points of this antitone-Galois connection on one side are consistent deductively closed theories. So what I'm saying that if I start with a consistent deductively closed theory and then I make this circle, then I will recover my original theory. If I keep making this circle again and again, nothing will change.
So if S is deductively closed, then this will become an equality. Right?
Yes, it will become an equality. Yeah. S is equal to theory of models of S. And on the other hand, also you will get something. Now, I want to connect this. So this is the most general syntax semantics duality. This is my syntax side. And this is my semantics side. The most general syntax semantics dualities I already mentioned, they are dual adjunctions, which means I have an adjunction between C op and D for two categories, C and D. All right. Now I want to connect this with the previous stone duality, and I will show you how that both of them can be connected together. So given a deductively closed theory S, consistent theory, yeah, subset of F, you can check that S is closed under its natural logical equivalences. S is closed under logical equivalences, which means if alpha is logically equivalent to beta and alpha belongs to S, then beta also belongs to S. Now you can ask me what happens when I take S modulo this inside F modulo this. Now, first of all, because it's a consistent theory, then a contradiction will not belong. So it means it is a proper subset of that Boolean algebra. Then it is naturally closed under all the upper bounds, all the consequences, and it is also closed under finite joins. So which means, in other words, this is a filter. A deductively closed consistent theory is a filter. Okay, yes. What this S? Okay, how it is filtered. So if I'm given any two formulas alpha and beta in S, if it is deductively closed, then can I conclude alpha meet beta? Yes. So this collection of logical equivalence classes of formulas of S, formulas in S, that is closed under finite meets. It is closed under all the implications if alpha is in S and beta is a logical consequence of alpha, then beta is also in S. It is deductively closed. Yeah, so using modus ponens, that is also true. And it is a proper subset because it is consistent. So it is a proper filter. Okay, so now that we have a proper filter over here, I can define an equivalence relation. I mean, say U. I can quotient out that Boolean algebra. Yeah, this can be defined. So say that the class of alpha is U equivalent to class of beta if S proves that alpha and beta are bi-equivalent. This is an equivalence relation. You can easily verify that. And then I can actually check. And this is not just an equivalence relation. Moreover, it's a congruence relation. A congruence relation on an algebraic structure is an equivalence relation which is well behaved with respect to all the operations of that algebraic structure. So you can check that this is really well behaved with respect to all of them. And therefore, I can define, if I start with this Boolean algebra, then I can quotient it out by this relation, and this will still be a Boolean algebra.
So you're extending tilde to F over
Yes,
Xi.
that will work as well. Yes. It is also compatible with the already existing logical equivalence relation.
Right.
And this can be done. Okay, now I'm ready to state my final thing. Yeah. So I will start with a theory. I have fixed, theories in over a fixed set PV. Yeah, I'm not going to change that. From that, I can associate to it a Boolean algebra. Then from that, I can obtain a stone space. And from that stone space, I can obtain the class of structures by simply forgetting that I ever had a topology. Okay, so this is the forgetful functor. From here to here, what I'm going to do, if I'm taking a theory, then I'm going to generate a filter out of the equivalence classes of those formulas in the theory. Means I'm going to, so this is a theory, let's say S, then S generates U. You close it under deductions and you generate U. Then you associate to it this F modulo this, quotiented out by this relation. Then you have this functor, which is already there. It is the stone space functor or blank 2 functor. And then you forget it. This is precisely your class of structures. And on the other hand, you simply associate the common theory. Yeah. This is simply the common theory of that. So this diagram commutes. I mean, sorry, not diagram commutes. This is when you restrict to consistent theories, then this is a perfect adjunction. And moreover, this is a contravariant thing. Stone is contravariant, right? This is contravariant. Forgetful functor is covariant. And this is also covariant. Now let me explain what this means, this last part, that if I take S1 subset of S2, then the corresponding filters are going to be also contained like that. And here we will get that F modulo this, modulo tilde U1, to F modulo equivalence relations, modulo tilde U2, there will be a Boolean algebra surjection. When you map to stone spaces, you will get inclusion Yeah, not all valuations will be there, but you will have inclusion of a smaller topological space into the larger one. And then you simply forget that you ever had a topology. You just take them as sets. So this is how this process works. So in particular, you can see that the stone duality is a syntax-semantics duality. That was the whole purpose of this discussion. Any questions? If I don't assume f is consistent, then we'll run into degeneracy problems. If f becomes inconsistent, then when you quotient out by this equivalence relation, you will get a single element Boolean algebra, which we don't want to deal with. We always want to assume 0 is not equal to 1. That's why consistent theories. And also on the other side, I'm not taking the empty set is not allowed. You can extend it formally by sending the empty set to, the singleton Boolean algebra to the empty set, but it doesn't make sense really.
But in any case, if that is inconsistent also, the similar procedure works.
Yeah. Formally, yes. It doesn't have any meaning. Yeah. Any questions? Yes.
Yeah, the equivalence relation you defined on U, like
Yes.
how it will reduce classes in F mod equivalence.
I think your question is more of algebraic nature. So yeah, the one way of answering that question is, look at this. I always like to think of Boolean algebras in the diamond shape. Yeah. Then this is my bottom element. This is my top element. What happens is that this relation, that there is a filter over here. Yeah. This is the filter U generated by my consistent theory. Then I'm going to divide at each point. I'm going to have these classes, and these classes are going to partition my whole Boolean algebra into different classes, and those classes will form the elements of the quotient Boolean algebra. If you if your question is of more algebraic nature, then you have to verify it. I don't want to do it in the class.
No, it's like the alpha, which is like equivalent to beta under U relation.
Yeah.
Won't it be already equivalent in F?
There will be more alphas and betas which are not logically equivalent, but they are equivalent modulo the theory S. So that's why there is more collapsing happening.
Yeah. So that's what I'm asking. Like, maybe example would help.
Okay, so any two formulas in that consistent theory will become identified in the quotient, if that makes sense. If I take any 2 points over here, then even though they are not logically equivalent, they are distinct points, modulo theory, that they will become equivalent eventually.
Yeah, okay. Any two formulas in S will be equivalent in modulo. Yeah, okay.
Yeah.
Am I correct?
Yeah.
Yeah, okay. Thank you.
S equivalence, but I'm just completing it to a filter, and then I'm quotienting out by filter. That's a more algebraically suitable procedure. Yeah. Manan. It has topology. Stone space has topology, and here you just have a set. So you forget the topology. That's all. Any other questions?
There is a question by Suyash on the chat.
Suyash, you can talk. Yeah, that's better. Okay, anyway, I will read it. Can we also replace theory blank in this final diagram by Clopen functor? I would prefer not. I have fixed the set of propositional variables. Then so it's rather the common theory that, and I want to emphasize on this particular example, Suyash, because I'm going to do something similar for first order logic in later lectures. Yeah, that's the whole purpose.
Okay, sir.
Okay. Right. So let us go ahead and I will take you back to some category theory now. I will need something more. I mean, maybe I have 15 minutes. I will talk a bit more. Right. So yesterday, Purvita started talking about terms, formulas, and so on and so forth. I want you to, I mean, if you are taking the first course in logic, then at least you should start thinking about what you are thinking. So if I tell you something like this, x square plus y square minus 1, what is the first thing that comes to your mind? Circle? Yeah, Vineet is saying circle. Anything? Anybody else? It's a polynomial in 2 variables. One other answer. Any online participant?
Circle itself.
Circle itself. So our brain is actually quite confused. It makes associations between different things, even if we don't need to. So I'm going to write down 4 different things. Yeah, x square plus y square is equal minus 1. Then x square plus y square minus 1 equal to 0. So perhaps x square plus y square minus 1 equal to 0 is closer to being a circle than the first expression. Right? Then also a rule, an assignment which takes AB to a square plus b square minus 1. I haven't said from where to where. And on the other hand, the class of all points, the set of all points such that a square plus b square minus 1 is equal to 0. Now, if in particular I choose this from R2 and then I get a function from R2 to R, and over here I choose this from R2. So basically I get a subset of R. This whole thing is a subset of R. Let me erase this, and I will choose these points from R2. Then this whole thing will be a subset of R2. Then finally, here you have a circle. But earlier 3, they are not really circles. What is this? The first one, the top left corner, that is simply a polynomial expression. It is a formal expression. It doesn't mean anything. So don't assign meaning to it. Don't read between the lines. The second one is simply saying that one expression is equal to another expression. We don't even know what equal to means. Yeah, this is just equality of 2 expressions, a very formal thing to do. And the third one is a polynomial function. It chooses 2 elements from a set. If at all there is a meaning associated to the symbols plus and dot and minus and 1, then it can generate a new element of the same set. So you need a structure. You need a structure with the interpretation of all these 4 symbols. My structure could be very stupid. I can start with a 2-element set. Then multiplication could be min. Then addition will always give me constant element 0. And yeah, anything. Yeah, it's really random. So it doesn't really mean anything. As long as I have an interpretation of all these symbols, then I can take 2 elements and I can generate 1 element. So it's a function from that structure square to itself. And finally, when you look at this, then it is a subset defined by the formula x square plus y square minus 1 is equal to 0. Okay. So as you have seen in yesterday's lecture, this is a term. This is a formula. Right? Then this is the interpretation of term. And finally, this is a definable set.
Isn't it interpretation of Fi to F1 2?
It is interpretation. Yes, interpretation of a formula is also another name for that.
Okay.
Okay. So these four are different entities altogether. Do not confuse them. If you are always thinking about real numbers or complex numbers, then yes, that's okay. But otherwise, do not confuse them. Yeah, this expression doesn't stand for a circle. Right. In general, now, the interpretation of a function symbol, if f is a function symbol with arity n, then the interpretation is going to be from m to the n to m. It is an arity n function symbol. Now, similarly, this term I'm going to write using a slightly different notation than yesterday, txy. So this is a term in context x and y. xy is a context suitable for this term, which means the variables which appear in this term are taken from x and y. You don't necessarily have to use all of them, but they are taken from here. Similarly, this is a formula in context xy. And this is interpretation of a term in context xy. So txy, or I can write t, the interpretation of t in m is again a function from however many variables are there in the context. Yeah, there are two variables, so m square and then m. So what I want to emphasize on is that interpretation of a term behaves exactly like a function. It's an n-ary function symbol. It's a generalization of function symbols, interpretations of function symbols. They will be interpreted as n-ary operations. On the other hand, if you look at a relation symbol, if I look at a relation symbol that's less equal on real numbers, then that is a subset of r cross r. Correct? So it's a subset of r square. It's a binary relation. Similarly, the formula phi in this context, context xy, the interpretation of that, so phi m, is going to be a subset of r cross r. So a formula, the interpretation of a formula is a generalization of a relation, and interpretation of a term is a generalization of a function. Fix this in your mind, yeah, very clearly.
The term is just an expression.
Term is an expression, but when interpreted, it is an n-ary function. A formula is again a formal expression, but when interpreted, it gives you a subset of some appropriate power of the domain of discourse, right? Or of the universe. This is really important. Now, in categorical logic, what we are going to do, we are going to interpret function symbols as morphisms from m to the power n to m. Now, what is m to the power n? That's why we studied products. M to the power n is n-fold product of copies of m. And on the other hand, the formulas will be interpreted as monomorphisms. Monomorphism is an appropriate generalization of injective functions. Yes, being a subset is nothing but there is an injective morphism from less equal to r square. Yeah, it's injective.
Formula is injective from where to where?
Yeah, it's here. So the relation less equal on r, that is the graph of that relation. It is in fact, and there is an inclusion of that into r square. The graph of that is precisely all those pairs of real numbers where x is less equal y. That is a subset. Subset means there is an inclusion function from there to r cross r. Any other confusion about this? So relation symbols will be interpreted as monomorphisms. So we have to deal a lot. I know there are only 5 minutes remaining. Yeah, so we have to deal with monomorphisms, and I'm simply going to give you a definition to think about, and tomorrow we will explore it a bit more. So one first simple exercise. Yeah. So given a pullback diagram, A, B, B prime, M, F, P, this, and let me call them M dash and F dash. Pullback diagrams we usually write like that. If M is mono, I have already expressed that, then so is M dash. Yeah, this is an interesting exercise. If you want to understand limits properly, we are going to talk more about limits in the second part, like category theory discussion. So whenever I say this is a pullback diagram, then the only given information to me is B dash, A, B, and M and F. That's all. This is given to me. Then I have to construct the pullback, which means there will be a cone with legs M dash and F dash and object P. This triple is my cone, and this is a universal cone in the sense that any other cone like this factors uniquely through this cone. Yeah, which means if I have this other object D and I have these morphisms such that it commutes, yeah, the whole diagram, the outer square commutes, then there exists a unique factorization such that both these triangles commute. So it's a very good exercise to show that if M is monomorphism, then so is M dash. This is really important for us. And if you are interested in monomorphisms further, then there is another exercise that a morphism M from B dash to B is mono if and only if B dash to B, B dash to B dash to B. This is M, this is M, this is identity on B dash, and this is identity on B dash, and this is a pullback diagram. A morphism is a monomorphism if and only if its pullback along itself is identity or an isomorphism more generally, because you know that pullbacks are not necessarily unique, but they are unique up to a unique isomorphism. So these two are very good exercises to warm yourself up to more category theory that will come tomorrow. So I will describe in tomorrow's lecture, I will start by describing what are sub-objects. So sub-objects are the right generalizations of subsets in sets. Monomorphisms are injective functions. Sub-objects are subsets. And then on sub-objects, you can have lot of order theoretic structure. And that is how we'll connect it back to the lecture by Professor Sujata Ghosh, that in general, you just have a partially ordered set. Then if your category has richer and richer structure, then you can define more and more structure to this subobject posets. If your category happens to have finite limits or pullbacks in general, then your subobject lattice poset will be a meet semilattice. You will have intersections of subobjects. If it is a coherent category, you will have unions of subobjects. So it will become a lattice. if your category happens to be the category of sets, then you have a Boolean algebra. Yeah, all of us know that the power set is a Boolean algebra. If your category is an iting category, I'm just throwing this word in right now. If it's an iting category, then the subobject lattices will be iting algebras. So iting algebras are the basic algebras used in intuitionistic logic, which you will see in next lecture later. So the richer the categorical structure, the richer the order theoretic structure on subobject posets. Yeah, this will be the beginning, and that will help us to interpret different connectives. The connectives are, let's say, meet. Yeah. So if every formula, if formula phi1 is interpreted as a monomorphism, formula phi2 is interpreted as another monomorphism, then phi1 conjunction phi2 will be interpreted as the intersection object, the meet of those two objects in the subobject poset. But for that, you need to have sufficiently rich categorical structure. So the richer the categorical structure, the richer the class of formulas that you can interpret in a category. So that will form the basis of our categorical logic. Yes, somebody had unmuted their mic. I could hear that. Anybody has any question?
In the definition of pullback, we have the pullback is unique up to unique isomorphism.
Yes.
Why is it unique up to unique isomorphism?
The
Like,
proof
why
was
did-
done yesterday.
why
Watch
was-
the YouTube
No,
video.
no,
I
no.
don't want to
As in,
do it. Yes.
no,
tell
my
me.
doubt is in the definition. Why is it unique up to unique isomorphism?
Because of uniqueness in the definition of the limit itself. Whenever I gave you this cone D, a cone with apex D. Yeah, that cone factors uniquely through P. So that H is unique. I mean, there exists a unique H. That H is unique.
Okay.
And that uniqueness will provide the unique isomorphism.
Okay.
Yes, you had a question? Okay, yeah. Why do I want to interpret? There are various reasons. So, for examples, I would like to study something like natural numbers or real numbers in a different category. So, generally, people have got people developed interest in this because of the method of forcing. The method of forcing was used to show that some statements in set theory, like axiom of choice, continuum hypothesis, these statements are independent, which means you can either assume that axiom of choice is true and you still have a consistent theory, no contradiction can be arrived at, and you can assume that axiom of choice is false and still no contradiction can be arrived at, assuming the rest of the axioms of ZF. So in that sense, what people wanted to do was to construct new models of theories, of set theories. So this was the original motivation behind trying to interpret different formulas in categories other than the standard category of sets, because once you want to understand something about set theory itself, yeah, you cannot use the same set theory and do that. You want to construct something new, and then what is the interpretation in there? How do you say that negation of axiom of choice is valid in a particular category? So you need a method of interpreting it. That's why categorical semantics. If you interpret the theory of groups in the category of, let's say, differentiable manifolds, then you will get Lie groups. If you interpret them in the category of topological spaces, you will get topological groups. So like in a very nice way, these different structures, mathematical structures, will get combined together. So in that way, you'll get a richer class of objects to work with. We are going to see some of it, but because I realized while giving this tutorial on category theory that not everybody is familiar with this. like very comfortable with the language of category theory. I decided to go slow, and today's lecture I totally devoted to stone duality. This is the baby example of categorical syntax semantics dualities. We'll do one more, and then maybe I will just point out what else can be done in general fragments. Yes, I'm going to end.
Yeah, so we are having a category theory discussion session after this. So
Yes.
if there are more questions, you can address them there. We are running out of time.
Yes.
So yeah, now we'll end this session and we'll come back after 10 minutes.
And I really want to encourage everybody to ask questions and participate in the discussion.
Yeah, so we might thank the speaker. And one announcement today at 5:15 p.m. IST. So all the regular online participants are requested to switch on their cameras. We'll have a photography session.
Not photography session, we'll take one picture or two.
Thank you.
Thank you. Thank you. मुझे लगता है ये हम सेशन बोर्ड पे करते हैं। तुम्हें थोड़ा ज्यादा काम होगा। There is no need. I am sufficient to handle it.
She has messaged me as well. She has messaged me as well. I don't know whether she will read it or not.
नहीं तो एक बार फोन करो। हेलो हेलो उल्टा लगाया था ठीक है people ran away yeah. I hope I couldn't see that the general consensus was that category theory is easy or something so
how many people were there? Now it is 50.
There were 29 yeah earlier I don't know oh I also have a list of topics if nobody talks then I mean there are certain things which have to be passed across yeah you cannot avoid them oh 16 good there's no need to chair. This is a discussion session. You want to be the moderator? Moderator of the discussion.
Yeah, why not?
But don't hold the mic. We need mics.
No, I just announced it.
Okay, fine. Announce it then. We can start. Press 5 and then be on the dais. Yeah.
Yeah, so we'll begin with the second session of the day. So unlike the previous talks, previous sessions, so this will not be a talk, this will be a discussion session on category theory. So if you're not familiar with abstraction, you might be having a lot of questions about category theory, which you may address in this session. And 3 of the speakers will have something to discuss and they will also do so. And always feel free to ask any questions that you may have. So yeah, over to you.
Thank you. Can you spotlight Isla for everyone? Okay, fine. So maybe not just for me, that's okay. Right, so Acha, but you don't have 2 chairs right now, so let's see. So to begin with this, what is really category theory and why did it begin in the first place? Can anybody answer that? Like, let's have a discussion. What is your idea? What kind of history have you read and what kind of purpose does it serve? Anybody from audience? We want to get more things from the audience.
Some sort of communication between different areas of pure mathematics or
okay.
Like they talk to each other in some way, they communicate with each other.
Right. Anybody else? Establishing relations between 2 to 3 theories in maths. Yeah, I mean, what is your guys' opinion?
The original history was, as far as I'm aware, is quite different. It started from homological algebra, where certain complications in calculations gave rise to natural notions of diagrams, first of all, like commutative diagrams. And then I think the whole category theory really started with the paper of Eilenberg and MacLean on a general theory of natural equivalences. I think that was the title. So from there, they began the whole theory that we covered, all except the adjoint adjunctions, was covered in that paper, in which their main aim was not to actually define categories, as far as I'm aware. Their main aim was to define the notion of a functor, the notion of change between two sort of different mathematical words. Yeah, so these are some historical considerations. The actual, if you sort of want to pinpoint the birth of category theory, it is pretty much in the land of homological algebra.
Deepankar?
I have nothing to say about this.
Why? No, you don't like
No,
history?
I don't like history.
Okay, fine.
Homological algebra is originated by the chains and cochains.
Yes.
Yes.
I mean, algebraic topology.
Yes.
Yes. Algebraic topology is the birth. Correct. Yes. Algebraic topology is the birth point, and diagram chasing as a technique. That is more fundamental than the notion of a category. So I would, yeah.
I looked at all these things and made it category.
Yes. So there are certain assignments. Yeah, you assign. So fundamental group, let's say, fundamental group assigns a group to a topological space, and it so happens that this assignment behaves well with respect to morphisms, which gives rise to functors. So assignments, object assignments, morphism assignments, they are more fundamental object. They are more fundamental than the notion of a category, the notion of a functor. And then eventually, this is our second topic, I mean, we'll transport there, that category theory started providing an alternate foundation for mathematics. There was also already this Russell's paradox lurking in the background, that the collection of all sets is not a set, because a barber who doesn't shave those who don't, who only shaves those who don't shave themselves. Yeah, this barber's paradox. So category theory tried to get out of it. Although in many senses, you are still tied to some set theoretic universe if you want to deal with this. But there are ways around it, and still I would say that category theory has reached more lengths than just set theory in generalizing some constructions. For example, the category of all categories, yeah, you can define it. Because at a time, you only need to look at a small collection. You only need to look at what is a functor. Given any category, given two categories, object to object assignment and morphism to morphism assignment. At that time, we don't really care about the size on both sides. Size is never the issue. It's mostly about how assignments are happening. And therefore, categories can themselves be thought of as objects, and morphisms between them are functors. And at that time also, like for the purpose of, like we all three have had a lot of discussions. So for the purpose of this course on basic category theory, we have said that category is a collection of objects. We were deliberately ambiguous there. It's a collection. We don't specify whether it is a set or a proper class or what kind of set theory we are using. But we said that homes form a set. Okay, so that we have done. When you go to the category of categories and functors, then that condition will not hold. But still it's a category in its own right. Yes, anybody from the audience who wants to say something? Offline, online?
So I have a doubt. How are we safe from Russell's paradox when we can have constructions like categories that only contains category which do not contain themselves?
How are we what?
How are we safe from Russell's paradox? If we can have a category.
Actually, we don't require anything like home sets. We do not require anything like home sets being sets in general. You can still deal with a lot of things without that. See, while answering this question, I want to bring to your notice that even in set theory, the notion of a function is more fundamental than the notion of a set. Function simply chooses one element from one collection and assigns to it a unique element of another collection. Here, you can also define functions which have proper classes as domains and classes as codomains. It doesn't really matter. The notion of an equivalence relation is more fundamental than the notion of a set. For example, we all know that sets have cardinalities. If you assume axiom of choice, then when are two sets equinumerous? If you have injections of one into another and the second one into the first one. So that is Schroeder-Bernstein theorem, assuming axiom of choice, that defines cardinality. Now, here the collection of all singleton sets is also not a set. But still, the notion of equivalence relation is undeterred. It is more fundamental than the notion of a set itself. So similar is the case, and that's why this should answer your question, Suyash. I feel that you don't really care about the sizes.
No, sir. My doubt is like, what is stopping me from considering the category of all categories which do not contain themselves?
No, nothing is stopping you. That's the answer. You can do it.
So wouldn't I get a contradiction like that category cannot contain itself and therefore it should contain itself and all that?
At that time, see, that's why I said like, whenever I teach a course on category theory, this is usually the direction in which it goes. Yeah, there is a lot of discussion on Russell's paradox and all. There are ways around it. That's all I can say for now. There is a notion of Grothendieck universes or von Neumann universes, and you can go in that direction and avoid thinking about it as a paradox altogether. Right, Vineet, you had a question.
My question was similar to Suyash, that
Okay.
what are objects and what are exactly
You just need to know what property defines an object. So for example, if I'm talking about groups, then I just need to know what is the property. I don't need to worry about how many groups are there. I just need to know, like between two groups, I just need to know what is a group homomorphism. I don't need to know how many group homomorphisms. Size is not the issue. It's not fundamental to the notion of a category. You want to add something?
I mean, here's a question that I think is more general than what you ask. Do you ever ask what do you mean by a vertex in a graph?
Yeah, exactly.
Exactly.
So as Professor Mahua Banerjee pointed out, that there are certain things which you cannot backtrace. You assume something as axioms. Have you heard of Munchausen's trilemma? This is one of my favorite statements. The audience may contain some members who are fond of the Big Bang theory. In one of the episodes of the Big Bang theory, yeah, you got this dialogue about Munchausen's trilemma, that either the statement can be predicated upon a series of statements, and that list is infinite. So A1 is true because A2 is true, A2 is true because A3 is true, and then this list continues indefinitely. We cannot do anything about that. Yeah, we don't have enough lifetime to keep justifying our arguments after we are dead. Then there is another way of arguing that eventually the arguments will start circling back to itself. A is true because B is true, B is true because C is true, and C is true because A is true. Again, this doesn't give you anything interesting as such. So that's why we have chosen the pathway of only looking at the statements which end at statements which you don't question. These are known as axioms. So similarly, category theorists have also made peace with set theorists by assuming Grothendieck universes, and they work with that. So Grothendieck universes is an increasing set universes of is an ascending chain of universes of sets where the notion of proper class and set is relative. The entire collection V0, that's a proper class when you look at it from within V0, but it is simply a set in V1. V1 is a proper class when looked at it from inside V1, but V1 is is simply a set in V2 and so on. So you have ways around it. Okay, so I want to bring your attention to the next thing, that it's a foundation for mathematics, but while doing so, category theorists were very careful about making sure that all the constructions which you could do in sets, they could still be performed in a category. Any examples from the audience? Cartesian products, yeah. Cartesian products had some property which could be abstracted out in an element-free way. This is the key, yeah. So first day, Deepankar, you mentioned something about society, right? Was a category is like our society. Yeah, in this classroom, all of us are sitting, we are interacting with each other. What is inside us, our physiology, has nothing to do with our interaction. It might have some impact on that, but we don't interact with the blood vessels and our hearts and livers. Yeah, we only interact with on a human level. So the internal structure is irrelevant. And that is the whole philosophy of category theory. Don't look inside. As Animesh asked the question that what is the vertex of a node? You don't ask that. You don't ask. So generally in naive set theory in your 9th and 10th standard, you have seen that sets contain elements. What happens when you take a course on set theory? Then you know there is no distinction between set and an element. They are all at the same level. And then things become more abstract, more complicated. But we don't want to go into those details. So category theory will try to avoid doing that. It doesn't have, the objects do not have any internal structure. In fact, objects can just be replaced by identities. And you can only talk about morphisms and forget about objects at all. And there is a way of writing it in a one-sorted theory, as a one-sorted theory. So this lack of internal structure is the defining property of a category. So that's why, I mean, does one of you want to discuss what an element is? Element of a set.
Well, at least in the sense of categories, I feel that yesterday I already talked about this. An element is nothing but a map from the terminal object to the set X. So if you want to think of X, then it is the map, let's say X bar, which sends star. At least in the sense of categories.
Now, what will happen if you replace this definition, I mean, continue with the same definition in the category of groups? Can you write down?
Yeah, then you would similarly try to think of, well, let's replace this by the terminal object and think of maps from the terminal object to X. You should do that, but yeah, but there is a problem maybe that this might not turn out to be a group homomorphism.
No.
If you
you are choosing a morphism.
Yeah.
Why are you saying it may not turn out to be a morphism?
If you take just an element.
No. It has to be if your definition happens to be that take a morphism from the terminal to the object, then in this case, there is a unique morphism, because in the category of groups, this also happens to be the initial object. So there is a unique morphism which takes identity to identity. So you don't really get an element of the group.
Only the identity element.
So what is the way out? How do you access elements in general? So that's why the new notion is that you don't talk about elements. You say if G is any general object, then an element of set X is simply a morphism. That's all. You talk about all the morphisms reaching G, and then somehow you assume, hope that the internal structure, if at all present, is hit by one of the morphisms, and that will take care of it. All morphisms, yeah? You cannot, so this is called a G element. A morphism from G to X is a G element of X. Any questions or comments? This is meant to be a discussion session, not a silent meditation session. Come on, speak up.
I had a question, but it wasn't related to this.
Okay.
So it's a question on ideals and filters. So how filters, I sorted how filters play an important role in overall logic and category theory, but ideals don't, I didn't see ideals to play an important role anywhere in the picture.
You can't
even though
define
ideals
ideals.
and filters are duals of each other in some sense.
Only in certain special cases you can, if you do not have the full lattice structure, then you can define only one of them. That's the first thing. So break your ideas that that's no. So if you only have a meet semi-lattice, then you can only define filters. You can't define ideas. If you have a joint semi-lattice, then you can only define ideas but not filters. Yeah. So in that sense, yeah, these are not really duals, and if you are talking about ideals in category theory, they can still be defined in abelian categories.
Yeah.
Any other question? Any other topic that people want to talk about? Any question that you might have by listening to the first 3 abstract lectures on category theory? Because those lectures only gave you definitions and examples.
Hello.
What do we do with category theory?
What do we do with?
Category theory and what is its kind of purpose? Like group represent,
What is the purpose of a group?
it represents symmetries and
Okay, so
groups.
does every group represent symmetry somewhere? Yes, by Cayley's theorem, I think. Yeah, it does, but that's a representation theorem. So you are again going back to the roots. Why was category theory introduced? And I think we tried to answer that to our best capacity. There was one more question from the audience, some lady.
Hello, sir.
Yes.
Actually, in before session, you talked about representable functor.
Yes.
So can you elaborate it with simple example? I get the definition, but I cannot totally imagine it.
A representable functor. Okay. Sure. So let me do this. Can you read this?
Yes.
The forgetful functor from the category of abelian groups to sets. Yeah, you consider this functor. What does it do? It takes an abelian group G and maps it to the underlying set G. Okay, now if I want to think about this in a more category theoretic manner, then this is precisely home in the category of groups, abelian groups from Z to G. There are many concepts hidden in this particular expression. Yeah, a morphism from Z to G is uniquely determined by looking at the image of 1. If I know where 1 goes, I know where 2 goes, where -1 goes and -5 goes, right? So that's definitely there. So this is going to be a home set. Home set will map to sets, and this is in one-to-one correspondence, I mean bijective correspondence with G. So actually, this forgetful functor, which we denote by U, this U is naturally isomorphic to home ABGR Z blank. So the forgetful functor is in fact representable.
Okay.
And many forgetful functors are representable. It's a nice exercise to check which ones are and which ones are not. So this is really nice in the sense that we can still be working within the category, not look inside what is an abelian group and still recover the set. The set, the notion of set is external here, because the home set is an external piece of data. We don't have any internal structure to the group. There is one more question I had, like regarding this. Yeah, somebody can suppose I want to describe a morphism from Z mod 3Z to G. The domain is a cyclic group. Yeah. So I just need to send one somewhere. Can I send one anywhere? Or is there any restriction to make it into a group homomorphism? Divisible by?
The 3 must divide the order.
Yes, 3 must divide the order of the element of the image of 1. So this is restricted. So the image of 1 is restricted. It has some restriction to follow. On the other hand, if I replace this group by just Z, I don't really have any restriction. And this is really the meaning of free, being free. I just have to choose this generator and I can send it anywhere. There is no restriction. I have a free choice. That's why these free functors are defined. Associate to any set the free abelian group. Associate to any set the free vector space on that basis. Yeah, you have a natural way of extending things. Similarly, I will talk about this. Suppose G is any group, yeah, not necessarily abelian, and A is an abelian group. If I have a morphism from G to A, what happens if two elements do not commute here? What happens to them? Their images will still commute because we are landing inside an abelian group, which means we actually factor through the abelianization. Yeah, there is a natural map from G to G ab, and we factor through that abelianization. Yeah, I mean, this is G modulo the commutator subgroup. We factor through that. Now, this simple looking fact can be represented as an adjunction. What happens? Yeah, if I take the abelianization functor from groups to abelian groups. And on the other direction, we have got an inclusion functor. Then I will simply look at this diagram. See, adjunctions, if you look at only their definition, they might look scary. But there is a quote in Saunders-Maclean's working categories for working mathematicians. And it is really true that adjunctions are ubiquitous. This is a heavy word in English. Ubiquitous means they are present everywhere. Wherever you go in mathematics, adjunctions are present. So what this says is that this is left adjoint. In other words, we write that when you land inside the category of abelian groups, yeah, this is the home set from G-ab to an abelian group is in one-to-one correspondence with the category of, with the set of all homomorphisms from G to the inclusion of that abelian group A into A. This triangle is presented in terms of this bijection, which is natural. Well, this natural word is also very interesting. In category theory, okay, if you want to define certain assignment, then that assignment is natural or it doesn't exist. Which means it's either obvious or it doesn't exist. So here I would also like to quote one more statement by Peter Fried, that the purpose of category theory is to prove that if a statement is trivial, then it is trivially trivial. Okay, so yeah, worth laughing at, because what are we saying really? Trivial and trivially trivial, but that is really the purpose of doing category theory. There are no shortcuts here. So generally, once you understand the definition well, then checking out. So I'm not sure how many of you went back home and checked this Dekker's master's thesis. I did as part of homework. Yeah, I did that. And this Dekker's thesis has so many pages on the proof that this is a functor. All of you know what a functor is. Yeah. Now, so far you have seen that definition and several examples, but showing that something is a functor can take an enormous amount of time. But if it is natural, then whatever amount of time it takes, you just have to push yourself through it. The proof is straightforward in the sense that category theoretically not much is involved. It must work. After hard work, it must work. Or if there is no assignment, no natural assignment, then it shouldn't work. That's all. It's completely binary. So can one of you try to describe this vector space and finite dimensional vector space and dual and double dual again? Okay. Dual and double dual. Write down all those adjunctions. Let us say something more about it.
So you begin with on finite dimensional.
Finite dimensional, yes.
So we begin with finite dimensional vector spaces. Say for simplicity, real finite dimensional vector spaces. And we get another finite dimensional vector space. And how do we get that? Well, here's one functor. We take a vector space V, just vector space V, with all the structure implicit, and we make the following observation that all the R linear maps from V to R, which is usually denoted by the dual vector space is a vector space.
Okay, so at this point, I have a question for all of you. Is V and V star isomorphic? Yes or no?
Yes.
Yes.
Yes, it is isomorphic, right? Now write down V double star and write down how V and V double star are isomorphic.
So that's the single dual. The double dual functor takes V and maps it to our linear maps from V star to R. And the main thing that the reason why you said V and V star is isomorphic is because they have the same dimension. Now look here. I will construct. So one way to say that V and V star are isomorphic because they have same dimension is to say that they have a non-canonical bijection, isomorphism between them. But look at this map, which maps to V. Okay, from V to V, which takes an element V, and I need to. So this is small v, and I have to give a map from V star to R. And how do I construct this map? Is that now again V star is this, so it will take a map from vector space V to R, say F, and will simply apply the small v to it.
We call it the evaluation
map. So
evaluation at V.
Evaluation at blank, in particular evaluation at small v. This is an isomorphism.
And this is canonical
isomorphism.
This is a canonical isomorphism. So no matter what vector space you start with, you have a natural way of producing a map from V to V double star. Right? Whereas in the case of V and V star, even if we know they are isomorphic, there is no natural or canonical way of setting up that isomorphism. That is just an external piece of data. And therefore, we do not say that V is naturally isomorphic to V star, but V is naturally isomorphic to V double star. In the natural transformation, yeah, in every adjunction, as you can see here in this adjunction, when you complete this circle, then there is a natural transformation. Yeah, so from the identity functor on groups to the inclusion of the abelianization of that, which means this map basically, G to G-ab. This is a component of that natural transformation. This is always there. A similar thing cannot be said when you are going from V to V star. Yeah, this is not a natural map. So I just wanted to emphasize on the meaning of the word natural. It has to be canonical. It is obvious. It's staring at you and you choose it.
Hello.
Yes.
V going to the inner product with V is not natural enough. You don't call it natural.
No, not from the category theoretic perspective.
Okay.
Because you don't have
On
inner
vector
product.
spaces you have on R. You have.
Yes, I mean, maybe if you have more categorical structure over there, then you will call it something. So if I have to think about inner product, maybe it should be enriched over real numbers in some way, but not in the standard sense.
Okay.
Yeah.
So if we can extract the if we can extract the transformation from the definition of category itself, then we say it is natural in some way.
No, it has nothing to do with category as well, as such. See, it has to do with it being a natural choice. There
Yeah, so
should be
natural
no
choice is
choice
coming.
involved.
Natural choice is coming from the definition, like finite dimensional vector space. That's it. From
Yeah,
there,
but
natural
when
choice.
you are using some external piece of data that any two vector spaces which have the same dimension are isomorphic. But when you set up that isomorphism, lot of choice is involved. Whenever there is no choice involved, it's natural. That's an alternate way of looking at it. This evaluation map from V to V double star, that is natural. You don't have to think about it.
Does it mean there is no other way of going from V to V double star? Only the
I'm
way
not
you
saying that. I'm not saying that. But this is the most natural way when you are looking at double homes. Yeah, it's one home embedded inside another home. So in that case, it's natural to just think about it.
Okay, thank you.
Any other?
Hi.
Yeah.
So in the representable functor, so suppose f is a functor, and we can we say it is a representable functor if it is isomorphic to Hom of dash comma c. Now Hom of dash comma c satisfies all the limits, right? So then
Don't say satisfies. Yeah, it takes time to get used to it. Preserves all the limits.
Yeah, it preserves. Yeah, it preserves limits. So then we say even capital F will preserve limit. Now, what if some functor doesn't preserve some limit? Then can we say it is not representable functor?
Okay, so actually your question demands more explanations than the answer to the question itself. So see, a category may or may not have limits. Being representable has no connection with it whatsoever.
Right. It need not have initial.
That's the first thing.
It need not have initial object or terminal object stuff.
If your category happens to have limits, it's a covariant functor down to sets. Yeah, down to sets only. Unless you know enriched category theory, it's only down to sets. Then it will be, if it doesn't preserve limits, then it is not representable. That's a very easy judgment, easy conclusion from the knowledge that you have. Yes, that is true. But preservation of limits has to depend on existence of limits. And if the limits don't exist, then still you can define a representable functor. So these two are independent notions altogether. Okay, so another point that that should be explained, what is an equivalence of categories? Equivalence or isomorphism of groups means if G is isomorphic to H, G is a simple group. It doesn't have any normal subgroup, non-trivial normal subgroup. Then H is also simple. Being isomorphic is nothing but renaming the elements. Similarly, existence of limits and co-limits, that passage is free between equivalent categories, both ways. And the notion of adjunction was introduced to show that you don't necessarily have to pass on every single piece of information, because category theory already has this intrinsic notion of abstract duality, C and C op. Even if you can preserve, a functor preserves half of the information, then the rest, the remaining functor in the other direction can preserve the other direction. Like one functor preserves left adjoints, the other functor preserves, the left adjoint preserves co-limits and right adjoint preserves limits. So only preservation of one half of the properties is good enough. So adjunctions is the most natural setting in which we should work in general. Equivalences are basically fixed points of adjunctions. As we saw today, theories. Not all theories can be recovered, but the closure of that theory can be recovered while you complete the cycle along the adjunction. So adjunctions restrict to equivalences, but adjunctions is the most natural setting in which mathematics should be viewed.
Are equivalence functors exact functors?
That depends on how you define exact functors, Krishnendu.
It takes exact sequences to exact sequences.
Now, if I'm talking about the category of sets, then where are exact sequences coming from?
Okay.
Yeah, I mean, yes, if your question is whether a part of an equivalence preserves all limits and co-limits, then the answer is yes. Yeah, that's the correct question and answer for your thing. Yeah, exact sequences means existence of kernels and co-kernels, and you are preserving them. That's true. Anything else from here?
Yeah,
These
so
are
in abelian category, it's true, right?
Yes, yes. You want to talk about something specific? I still have got a list. So the constructions, the categorical constructions which you do in sets, what are those? Product, Cartesian product was one of the answers earlier. Then you wanted to talk about elements. We have a generalization of elements as a morphism with that codomain. Then you can construct disjoint union, that is coproduct, right? You can construct arbitrary products, arbitrary disjoint unions. Then another feature of sets, of the category of sets, is existence of power sets. If you do a bit more category theory, you will learn that exponentiation, exponential objects are also possible. I mean, in the case of sets, the exponential of b, like a to the power b, is precisely the home set from b to a. But that has some adjunction. So if you go into Cartesian closed categories or topos theory, then you will see more of this. Then another property which you have for, where is the chalk? I maybe forgot it. Okay. So about monomorphisms and sub-objects, I'm going to talk tomorrow. So I don't want to say a lot about it, but this is a different property. Well, today is the day of number 2. So I'm going to use number 2 once again. If I have this kind of situation, what is the meaning of a function from a to 2? It's a characteristic function of a subset, right? So given a monomorphism, so there is a one-to-one correspondence from subsets of A and home sets A2, which means this sub is a contravariant representable functor. See, this is such a beautiful result. You don't have to actually understand the concept of a subset at all. It is representable. And number 2 is again playing an important role. Huh? A third occurrence of number 2 here. And actually this can be completed. You can take a singleton over here, and there is a morphism which takes star to your favorite element, let's say 1. So this stands for the truth values. Yeah, this is true and false. I can take it to true, star to true. There is a unique map from A star to singleton because singleton is a terminal object. And this diagram is a pullback diagram. From a very simple looking expression, we can construct this pullback diagram, and this pullback diagram is the basis of topos theory. This 2 here, which is known as the object of truth values. Yeah, this is 2-valued classical propositional logic. 2-valued logic, yeah, these are the values. Here, in general, you have a sub-object classifier. Yeah, as the name suggests, it classifies sub-objects using the representable functor. And that subobject classifier is also the object containing the truth values. So if you want to study multi-valued logic, then you just have to change this object. I mean, in different categories, if you have a subobject classifier, it's unique up to isomorphism. And that will be the internal object of truth values. Now you might ask, the object doesn't have any elements, but you don't need to have. You can still do logic without having any elements inside, without accessing anything internal to it, but there are still truth values. Right? So tomorrow I will talk about the concept of an internal group object. You will learn more about it. How do you visualize these internal operations? You don't need to know what is inside. You just view everything externally. That's the whole point. Whatever constructions were possible with sets and functions and elements, you try to bypass them. Like simple notions such as a monomorphism, right? You have a f from A to B is a monomorphism if and only if whenever this is right, yeah, this direction is right. I'm really bad at left and right. You will experience that one day in one of my lectures, right? So whenever f composed with g and f composed with h are equal, then I can cancel f. So yeah, fg is equal to fh. I can cancel f. This is left cancellation on right cancellation depending on your choice. But this cancellation property is being monomorphism, which coincides with being injective. There is another way. Yeah, why category theory is more expressive. There is another way that if this is an injective function, then actually there exists a k. Correct? There exists a k which makes this like this identity. Kf is identity. This is known as a split mono. A morphism which has one-sided inverse. Yeah, Kf is equal to identity on A. This is known as a split monomorphism. Here I can list 5 different types of monomorphisms and categories in which they are different, but in the category of sets, they will all coincide. Monomorphisms, strong monomorphisms, regular monomorphisms, extremal monomorphisms, pure monomorphisms, split monomorphisms. They are all useful in different settings. They coincide. So in order to have a good grasp of abstraction, you have to understand that when 2 definitions are not equivalent. One more thing I want to point out, this I was going to do tomorrow, but since you are going to look at intuitionistic logic today, yeah, this is something very interesting. The concept of the important defining property of a field is that every element that is non-zero has a multiplicative inverse, right? So classically, these 2 statements are equivalent. Suppose I am working in a commutative ring, then this is one statement. And for all x, if x is non-zero, then there exists a y such that xy is equal to 1. Classically, these 2 statements are the same, right? But if you go to intuitionistic logic, then these 2 will be different. The fact is that negation A or B is not necessarily the meaning of A or B is not necessarily equivalent to negation A implies B intuitionistically. Which means there will be categories in which if you use this theory of fields, this axiom for the theory of fields, then that interpretation of fields will be different than this interpretation of fields. Very interesting, right? You can, so there is a new topic called synthetic differential geometry, in which you can construct a model of real numbers where every function from reals to reals is continuous. Every function. You give a requirement, you can construct a model. If you can axiomatize it, you can construct a model. So this kind of flexibility always lies with us because of this. Because of difference in presentations of theories. Differences in interpretations, differences in the strength of the categorical properties present in the category. So this is like a vast generalization of the category of sets. Yeah, so let me see if, are there any questions? Any comments from the audience? Okay. I'm not sure. Bhargav is saying something without unmuting himself. No, okay. Right. One more property which I think Deepankar talked about is the difference between structure and properties. Yeah, that is something which is worth highlighting once again. Yeah, the structure is, I mean, I'm just going to take a 2-element set, okay? This was the choice of Animesh at some point, and I'm going to define a binary operation M on this set. I did not put any thought in that. I just have some way of filling up this diagram. This is any arbitrary function. If I take the language consisting of one binary function symbol, then this is a structure for that. So if I start with the language of groups, then a structure for the language of group need not be a group. I still have to add the theory to it, that the operation is associative, the operation has an identity, the operation has an inverse. I still have to add that on top of the things. So which means forgetting the part of structure, when I go from a ring which has two different operations, when I go from this and I associate to it simply the multiplicative monoid, then I'm forgetting about a structure. If this operation is commutative, yeah, then forgetting that it was commutative multiplication, that's not a forgetful functor. You are not forgetting structure. Forgetful functors are precisely those where you forget structures. On the other hand, this is an inclusion functor, abelian groups to groups. If you put more restrictions, if you ask for more properties, then you will get a subcategory. And then in those cases, you will get inclusion functors, not forgetful functors. Whenever you study a domain of mathematics, please keep this in mind. What is the structure? Ask yourself, what is the structure? If I'm studying graph theory, then what is the structure of graph theory? The structure consists of the vertices and edges. The fact that it is a connected graph has nothing to do with the structure. It is simply a set of nodes and a binary relation, which is a binary relation, okay, not even being reflexive, irreflexive, and symmetric, which is our normal definition for a simple undirected graph. Those things do not come under this label. Okay, so always distinguish between structures. If you start with major theory, then what is the structure of major theory? You need a sigma algebra. Then you need a function down to real numbers specifically. The properties are irrelevant. Right? So this is what I'm talking about. Always try to identify. If you learn logic, at least the takeaway from this school should be that you should be able to distinguish between structure and properties. You should be able to understand what are the important operations. You should not ever call x square plus y square minus 1 as a circle in the future. Right? Because you are understanding the basics of how we think. So that's your, I'm open to questions. Otherwise, I will end the session here.
Yeah, any questions from the offline participants or online? If not, then we'll like to end this session. If you have any further questions, you may email Amit sir at his email ID. And now we'll end this session. We'll have a lunch break of 1 hour, 15 minutes, and we'll come back at 2 p.m. IST. So then Nick will talk about intuitionistic logic.
Yeah, today we are taking an early break because we have 2 more lectures, full lectures afterwards.
Thank you, everyone.